Hello students, in this video we have second exercise problem of chapter 5. Again, we have few questions. Very first question is, the Earth's magnetic field varies from point to point in space. Does it also change with time? If so, on what time scale does it change appreciably? Now we know that if we consider Earth to be a gigantic magnet, say this is Earth, then the magnet of Earth is supposed to be like this with South Pole here and North Pole here. So as you go from one place to another place, the intensity of Earth's magnetic field is changing, and hence we say that at different latitude and longitude, the intensity of Earth's magnetic field is not same. Magnetic field changes with place to place. Does it mean that the whatever magnetic field we have right now at given place, it will change after few years at the same place if we go and measure its magnetic field? Would it be same or different? Now Earth's magnetic field is changing with time also, and one theory says that this North Pole and South Pole, they swap their positions after few thousand years. So the South Pole and North Pole, they are changing their position, and hence the Earth's magnetic field at given place is changing with time. Now on what time scale it is changing? uh, what scientists believe so far is that the time may be 2000 year to 12,000 year for the poles to sweep their position, but there is no confirmed number that after what period of time the magnetic poles will be swept completely. But answer is yes. Earth's magnetic field is changing with time also. Moving to second question. The Earth's core is known to contain iron, yet geologists suggest that the source of magnetism is not iron. Why? Very simple reason. In Earth's core we have iron, but we have molten iron. And when you have molten iron, there are no chances of domains to form. And if there are no domains, it is not ferromagnet. If it is not ferromagnet, then you cannot say it is a magnet. So Earth's magnetism is not because of some gigantic magnet inside the Earth as shown in this figure. It is only for our understanding. It's not that we have iron inside the Earth's core and it is situated uh, in this fashion, and because of that we have Earth's magnetic field. No, it is not that. Iron is in molten situation, molten position, and it cannot have ferromagnetic domains. So there is no question of magnetism of Earth is originated due to iron. Okay. Moving to next, the charged currents in the outer conducting region of Earth's core are thought to be responsible for Earth's magnetism. What might be the battery, that is source of energy, to sustain the currents? Now one possible reason for this is radioactive elements, but again it is a theory. Next, the Earth may have even reversed the direction of its field several times during its history of 4 to 5 billion years. How can geologists know about Earth's field in such distant past? Very interesting question. It is believed that so far the Earth has changed its magnetic North Pole and South Pole. The poles are swept around 180 to 200 times in so many billions of years of Earth's history. And how do we know? The answer comes from geology. There are rocks which have stored the magnetic field direction in terms of their magnetism, in terms of their domains. So when we study such rocks, ferromagnetic rocks, we do realize the directions of Earth's magnetic field over different time period. Next, the Earth's field departs from its dipole shape substantially at large distance greater than 30,000 km. What agencies may be responsible for this distortion? At this distance, we have ionosphere, and in ionosphere we have different ions present, ions of different gases present. And as ions move, it is like current produced, so they have their own magnetic field which interacts with Earth's magnetic field, and hence some distortion in Earth's magnetic field is observed around 30,000 kilometers. It is because of ions present in ionosphere. Lastly, interstellar space has an extremely weak magnetic field of the order of 10 to minus 12 Tesla. Can such weak field be of any significant consequence? Explain. In the interstellar space, we have very weak magnetic field, and when charged particles pass through this space, they get deviated because of the this weak magnetic field. And during long journey, the deviation in their path is significant. Otherwise, this weak magnetic field is not of much significance. But when we talk about journey of large cloud of charged particle, it makes difference in their journey. So that is all about second numerical. Thank you.